workshop. Yesterday was mainly about geometry, and today it's mainly about algorithms. So to begin the session, we have Alice Pellet-Mary. That's the best I can do. To tell us about her work with Changmin Li and Damien Stelle and Alexander Wallet about an LLL algorithm for module lattices.
Okay, thank you. So the purpose of this talk is going to describe an algorithm. So the main objective is to try to find short vectors in structured lattices, in modular lattices. And so what I want to show you is an LLL type algorithm that works for modules in any number fields, where the approximation factor we get for the shortest vector is roughly exponential in the rank of the module, and the runtime is complicated, but it's roughly, assuming we have an oracle, it will be quantum phase. So let me go through the definition of everything. I want first to start with a bit of motivation. So why are we interested in modular lattices and structured lattices in general? So my main motivation is crypto. And schemes using lattices, most of them, they use structured lattices to improve efficiency, so to reduce the size of the public key and of the ciphertext. So if we take an example, and we take a look at the post-quantum standardization process of the NIST, currently we have 12 lattice-based schemes that remain at the second round, and 11 of them use structured lattices, so as I said, to improve efficiency of the scheme. And so how does it improve? So let's take just Frodo is the one that does not use structured lattices, and I compare it with one of the schemes that use structured lattices. And roughly in terms of size of the public key and ciphertext, we gain usually at least 10 in terms of the size of this one. So it really helps to get some performance schemes. And so this is, I said structured lattices helps improve efficiency of the schemes. In fact, if we look at this candidate, these 11 candidates using structured lattices, they all use modular lattices, which is a specific kind of structured lattice. So, that's the main motivation. We are interested in these modular lattices because they are used a lot for the current cryptographic construction. So let me now define what is a module. So I'm going to define first a module, and then I will tell you how this can be seen as a lattice. So a module is an algebraic object, and it lives in a number field. So number field here for me will be K. It's just the ring of polynomial with rational coefficients, modulo some polynomial P that is irreducible. And in this field, I have a ring, which is R, which is the ring of polynomial with integer coefficients, mod P. And so free module is going to be, so here is the definition. It's simply the set of all linear combination of a basis of linearly independent vectors. So this basis lives in the field, but the linear combination should be ring combination. So if you think about K as being Q and R as being the integer Z, this is just a lattice. And it's kind of a generalization of a lattice where you work in a number field and the ring of integers is Z of X mod P, or the ring of integers of a number field, instead of the ring of integers Z we are used to. So in a sense, a module is kind of a lattice over a ring R that is not Z, the ring of integers. So this is the algebraic definition of a module. And for crypto, we are interested in module lattices. So we want to see these objects as lattices. So we want to have some geometry on them. And for the moment, I have some algebraic relation, but I don't have any geometry on this. And so we're going to embed these elements into some real number field so that we get some geometry on this object. So how we do that? So this is just a reminder. We're going to consider an embedding that is called the canonical embedding that maps the field K to C to the D. And so I'm going to map a polynomial, so X, an element of K, is a polynomial mod P, so it's a polynomial of degree D minus 1, let's say. And so I'm going to map it to a vector where I evaluate this polynomial at all the different roots of P, all the complex roots of P. So this gives me a way to embed the number field into C to the D. And so this gives me some geometry on the number field. Now I can define the shortness of an element as the shortness of the vector. And same thing, if I have vectors in K, I'm just going to concatenate all the vectors obtained by embedding all the coefficients of the vector, and I get a big vector of dimension K times D. And this is now something that lives in a real vector space, so I have some geometry on this, and I can define it. Okay, so now what is a module lattice? I take a module as I described previously, and I'm just going to embed all the vectors of my module into C to the KD, and this gives me a lattice. So it can be shown that this is a lattice, so here is a basis if you want to be sure that it's a lattice. And so this is a lattice of dimension K times D in C to the K times D. So I kind of have a duality in modules. Either I can see them as lattices over Z with large dimension, K times D, or I can see them as lattices over the ring of integer R of small dimension K. So I have these two ways to view module lattices. And just to give you some orders of magnitudes for the schemes that I told you about for the Lewis competition, usually we want the dimension over Z to be roughly 700, 1000, so quite large. And the dimension as a module over K is very small. So usually 3, 4, never less than 10. So we really have something very small over R and a big dimension over Z. And so that's the duality of the two things. And if I guess most of you know the BKZ algorithm. So if we want to try to find short vectors in lattices over Z, asymptotically, we can have some trade-offs between how much time we are willing to spend and how short is going to be the vector. And so the best trade-off we have asymptotically is given by BKZ. So roughly, it's the blue curve. So the sum of the exponent should be 1. 2 to the n and 0, or 2 to the n 1/2 and n 1/2. And so this works for lattices over Z, depending on how much time we want to spend. And we have this specific point here, which is the LLL algorithm. And the LLL algorithm allows us, in polynomial time, to find a vector of a lattice that is at most 2 to the n times larger than the shortest vector of the lattice. And so this, as I said, is over Z. So over Z, my module lattice has a very large dimension. So if I use the LLL algorithm, I'm going to have an approximation factor 2 to the 700, so it's going to be super large. But if we could make it work for lattices over R, where the dimension is much smaller, then we could have an approximation factor much smaller. So that's the main idea the main motivation of what I want to try to show you, is can we extend the LLL algorithm, which works for lattices over the integers? Can we try to extend this to other rings? Because if we can, we would get much smaller approximation factors for module lattices. So that's really the motivation. And so I'm going to give you, so the answer is no, we don't for the moment. But we have been improving the status, the state of the art. So I'm going to show you this. But just let me maybe tell you a few words, because for the moment when I say LLL over R, I'm kind of assuming that I have something, I have a notion of shortness in the number field, which is not obvious maybe at the first sight, like in a number field. We don't really know what is short, so I already said that we can see shortness as shortness of the vector, because an element of a number field is a vector, so I can say that a short element of my number field is a short vector. So this is a first way to see shortness in K, but there is another way. So here are the two kind of natural ways to define shortness in a number field. The first one is take the Euclidean, the size of an element is going to be the Euclidean norm of the element when seen as a vector. So I'm going to call that the Euclidean norm of the element. And the second one is the algebraic norm. And so it's simply the product of all the absolute values of all the coefficients of the vector. So these two quantities, they have natural I mean, they have nice properties, and we are going to need both of them. And just a remark, like if we were over the real and over the reals, then these two quantities would be the same. I mean, the absolute value of the vector of size 1 and the product of the absolute value of the coordinate of the vector of size 1 is the same. But when we increase the dimension, we have two ways to generalize this absolute value. So that's it. And so let me also say one more thing. Controlling the Euclidean norm allows me to control the algebraic norm, because if this is small, then every coordinate should be small, and so the product should be small for some definition of small. The reverse is not true. So if the algebraic norm is small, it could be that one coordinate is super large and the other one is super small, but the product is still 1. And the Euclidean norm could be arbitrarily large. So this kind of gives me the intuition that it's better to control this norm because it always implies controlling the other one. So it's usually easier to work with Euclidean norm rather than algebraic norm. So I'm going to come back a bit to that later.
In terms of applications, does it matter? I mean, are there applications where controlling the algebraic norm is enough and maybe it's simpler? Since control the Euclidean norm is better because it implies the other one, like you said, but is it easier to control the other one but still sufficient for someone?
I have no example of where it would be sufficient. I mean, for the cryptographic application, what we usually want small is the Euclidean norm, not the algebraic norm.
Yeah, this was my question. I mean, are there applications where,
No, I don't see. And also, like what I'm going to tell you maybe a bit during the talk is that for instance, if we want to do LLL, so my objective now is going to be to minimize the Euclidean norm, not the algebraic norm.
But not in cryptography.
Yeah, okay.
In coding theory, for fading channels, we use the algebraic norm. Fading channels and minor channels. And this is in code.
Okay. And so, what I wanted to say is that for the LLL algorithm I'm going to show you, I really need to control both. So I cannot control only this one. It's not going to work. Depending on the steps of the algorithm, sometimes I need to control this one and sometimes I need to control this one. So, for now on, I'm going to mostly focus on the Euclidean norm because controlling this implies also controlling the other one. Okay, so we have a notion of small in K. So we can imagine what is LLL now over a number field. And so let me tell you a few words about what is known about generalizing the LLL algorithm to number fields and ring of integers. So basically what we want when we have an LLL algorithm is that it outputs somehow short vectors and that it runs in polynomial time. So here I've put two columns, quality and runtime. And so the first result we have about generalizing LLL to number field is due to Napias in '96, and she described an algorithm, but there is no proof that it's going to be polynomial time, and there is no proof that the output is going to be small. She was more interested into practice. She tried it, and it worked quite well for some small number fields she was interested in, but that's all. So the same year, Ficker and Post proposed also an LLL algorithm for all number fields, but same thing, they couldn't prove anything. And for totally real number fields, they can prove that the runtime can be polynomial, but then they have absolutely no bound on the quality of the shortness of the vector that is going to be output.
Bounded degree, or really all number fields?
They describe it for all number fields. And the algorithm is essentially the LLL algorithm, where you replace everything by final closed vector. So you can define it for all number fields. You can describe the algorithm for all number fields. It doesn't make it efficient.
They give themselves an oracle for Euclid reduction in the base field? Or?
Yeah, for instance, so basically they have a point, they say, okay, let's find the closest point in the ring of integer and reduce with that, essentially. Okay, so more recently there is an algorithm by Kim and Lee where they try to do LLL for norm-Euclidean fields. So that's number fields that are Euclidean for the algebraic norm I've defined on the previous slide. So something quite interesting here. Yeah.
Alice?
Oh, sorry.
How about the 2010 paper of Ficker and Stelle?
Oh, yeah, so that's, yes. So that's something different, so that's why I didn't include it. So what they do is they see the lattices, the modules as lattices over Z, do LLL there, and then reconstruct a basis of the module. But, so I could have probably put it there also, but then the shortness, like it's going to be exponential in the dimension over Z. And here I'm really interested in something exponential only in the rank of the module.
But so it would fit in this description with a crappy bound on quality.
Yeah, yes, yes, yes. Yeah, so something I should say here is I'm interested in trying to have something that is exponential only in the degree of the, in the rank of the module, sorry, and not in the dimension of our integer. Yeah, so for norm-Euclidean fields, they could prove runtime but not quality. And they have a slight different variant of the algorithm where they can prove quality but not runtime. So they can have either one or the other, but they cannot have both. And except for biquadratic norm-Euclidean fields. So norm-Euclidean number fields that are quadratic of quadratic extension. And this is here kind of related to what I told you, that controlling the algebraic norm does not allow you to control the Euclidean norm. And you kind of need both for the LLL algorithm. And so what I want to present today is an algorithm where we have short output. And the runtime is, what I mean by this symbol is it's going to be polynomial time, but provided we have an oracle that solves the closest vector problem in a fixed lattice. Yes?
What about the work of Camus, who generalized the Napier algorithm and technically keep exactly the same structure, but have just an improved analysis on the running time? Because I don't understand why you are saying that there is no bound on quality in the Napier's work. Because technically, I mean, it's very related to the biquadratic norm-Euclidean Kim-Lee algorithm because they keep the same structure and they have exactly
I think it's a
bound as Kim-Lee, but for norm-Euclidean rings.
So in Napier's,
you can have bound on quality. The bound on runtime is false. It's nonsense. But you have the same bound on quality for already in the journal version of Martinet-Napier.
Maybe I didn't read the good version. The one I saw, there was no proof on nothing. So maybe there is a journal version. Okay.
And precisely the work of Camus was to merge the Napier's Kim-Lee and technically L squared to have like a bound on the quality and a bound on and a polynomial time bound on the runtime for any norm-Euclidean number rings.
For any norm-Euclidean number field, you can have a bound on the two.
Bound on the you can have.
So because I've read Camus' thesis and it's only for quadratic number fields.
So maybe we could take this.
Yeah,
sure.
Yes. Okay. Anyway, so we have a lot of restrictions if we want to do LLL related to Euclidean or not, and sometimes it's not even sufficient, I think. I mean, depends. And so, yeah, so what I want to show you is something that works in any number field. And we need, so this is the main drawback. We need to have an oracle that solves a closest vector problem, which is something hard in general, in a fixed lattice, but this lattice only depends on the number field, not at all on the module in which we want to find short vector. Okay, so that's the plan of the talk. I'm going to dig more and more into the details. So I'm first going to give you a high-level overview of LLL. Then I'm going to focus on LLL in dimension 2, which is the Lagrange algorithm. And then I'm going to focus on a part of this algorithm, which is Euclidean division, which is important for LLL. And so it's great to zoom and zoom. Yes?
A question about the previous slide.
Yes.
So the bound inequality is merely exponential in the rank over the ring. Is that right?
Yes.
Some dependence polynomial or so on
And it's quasi-polynomial in the degree of the number field.
the ring. Okay. And if you had an approximate CVP oracle, for example?
No, it's going to be super bad. We can allow approximation factor up to an approximation factor of 2.
To 2. Okay.
After that, it stops working. It's not that it decreases the bound, it's doesn't.
Just lost. Okay. Thanks.
Okay. So let me describe LLL in a way that looks a bit like BKV, because that's what I'm going to mimic then for LLL over a ring. So basically, I'm going to see LLL as a combination of two algorithms. The first one is a reduction that goes from solving exact, so SVP is shortest vector problem, right? Finding the shortest vector, non-zero vector of so that use an oracle solving SVP in dimension 2, and using that solves gamma SVP in dimension k for an approximation factor that is exponential in k, in polynomial. So that's the first block. And the second block is the Lagrange-Gauss algorithm, which solves SVP in dimension 2 in polynomial time. So then if you combine both, you get a 2 to the k approximation factor in dimension k. So that's what we want to mimic over the ring. So we are going to have a reduction from gamma SVP in modules of rank 2 to gamma prime SVP in modules of rank k, where the approximation factor gamma prime is exponential in k and polynomial in the degree and in the first approximation factor. This is polynomial time. And the second part, which is the maybe more complicated one and what I want to spend the more time on, is how do we solve gamma SVP in modules of rank 2. So this, we achieve it not for exact SVP, but for an approximation factor that is a quasi-polynomial in the degree of the field. And this is a heuristic quantum algorithm, and the runtime is going to be, as I said, poly, only if we have an oracle solving CVP in the field lattice. Yes?
Is this only for the cyclotomic ring, or is this?
Oh, yes, sorry. So the numbers I give are the one for cyclotomic rings. For generic number fields, you need to change the numbers, but basically if you have a number field with the same discriminant and the same covering radius as cyclotomic, the number will be the same. Otherwise, it should depend on the discriminant and the covering radius of the number.
So what's the heuristic about the algorithm?
Hmm?
What's the heuristic part?
I'm going to show you the heuristic. But it's...
Performance or
What?
is it the heuristic running time?
So the heuristic is about the covering radius of this fixed lattice. We assume that there is a close point for the target we construct.
Sorry?
Yeah.
Assume that there is a...
We assume that the lattice we construct here, the fixed lattice, has a small covering radius in a sense. Okay, so as I said, this part is the one I want to focus on, but I'm still going to say first a few words about the first reduction. And the only thing I'm going to say about the first reduction is, so basically it's going to really mimic how the LLL algorithm works. And to mimic it, we need to have some QR factorization. Once we have that, we can mimic LLL quite easily. So the main technicality here is to define an inner product and some QR factorization over the number field. So here is the inner product we are going to use. So we have vectors of elements in K, and we define an Hermitian inner product, which is just AI bi bar. So here, bi bar, remember that an element in K is a vector, so I'm just going to take the conjugate of every coordinate of the vector. And I'm going to assume for this talk that this lives in K still. So this gives me some inner product over K. And I can also define the norm over K, which is the square root of this inner product of A with A. So again, I take the square root coordinate by coordinate. And so this gives me a way to kind of, so I have a vector of elements in K, and now I have only one element in K. And I can use what I defined as small for an element in K. So either I take the Euclidean norm of this quantity, and what it gives me is the Euclidean norm of A when I expand it as a very big vector. Or I can take the algebraic norm of this quantity, and what it gives me up to some, so delta K is something depending on the number field. But except for that, what it gives me is the volume of the module lattice spanned by this vector. So this quantity, this norm over K, captures both the length of the vector when I expand it and write it as a vector, and the volume of the module lattice spanned by this vector, which are the two quantities I need to control. Yes?
This non-quantity doesn't always lie in field K, right? Are you assuming that it would?
Sorry? The square root?
Doesn't lie in the field usually.
Yeah, so both for the conjugation and for the square root, I'm kind of making assumption that it is in K. It's usually not. So the thing is, we are not going to work in K, but in the completed field KR, where we just consider the completion with R of the number field. So we can take square root coordinate by coordinate. I mean, I'm really just seeing my vectors, my elements in K as vectors, and taking square root coordinate-wise. And I multiply coordinate-wise, I add coordinate-wise, everything happens coordinate-wise. But let's forget about this and just assume everything lives in K for simplicity.
What's L of A?
L of A is the module lattice spanned by A. Okay, and so now that I have this inner product, I can define QR factorization. So I'm not going to read the formulas. These are exactly the same as the one you would have over the reals. You can check. But so we can just define everything as we would have done over R. And we can factor the matrix B as some matrix Q times some triangular matrix R. And then what we get, I mean, the nice properties is that this is what we were expecting. Multiplication by the matrix Q is not changing the geometry. So in a sense, we can always assume that the basis is triangular because we just multiply by some matrix that does not change the geometry, and we get exactly the same. I mean, we get something triangular. So this is essentially the only thing that is needed for the reduction from rank 2 to rank n. And another property that is also useful in LLL when we want to show that the vector output at the end is somehow small is the fact that any vector in the module should be larger than at least one of the diagonal coefficients of R, and this is still true. So these are basically the only two properties we need, and once we have that, we can really mimic the LLL algorithm with this inner product, and everything is going to go through for the reduction from rank 2 to rank K. So I'm not going to describe how this works. Really, this is the only two ingredients we need to mimic it. So now I want to focus on the second part, which is how are we going to find short vectors in modules of rank 2. And let me first describe the Lagrange-Gauss algorithm over the integers. So we have a lattice of dimension 2, and we are given a basis of bad vectors. And here is the basis, so this is B1 and this is B2. So the first thing we do is we're going to rotate the lattice, rotate the space, just turn the head, so that B1 becomes horizontal, which on the matrix side means that we're going to compute the QR factorization so that we get a triangular matrix R. So now B1 is horizontal, and what I'm going to do next is I'm going to reduce B2 by a multiple of B1 to make it as small as possible. And again, on the matrix side, it means that I'm going to perform a Euclidean division of this non-diagonal coefficient by this diagonal coefficient to make it smaller than 1/2 of 10.2. So I get a shorter B2, and now I swap the two vectors, and I start again. So rotation so that B1 becomes horizontal, Euclidean division of -10/3, and now I'm good, I have a short basis. So that's Lagrange-Gauss algorithm, and there is two things that we needed during this algorithm. We need the rotation, so QR factorization, and we need the Euclidean division. Essentially, that's all we need. So the rotation, we have already seen that how to define QR factorization in the previous slides. So what remains is how are we going to have a Euclidean division? And that's the hard part because you probably know that in many number fields, there is no Euclidean division. So we don't have this way of reducing B2 using multiples of U1. So let me just give you more details on this Euclidean division and why it does not exist. So over Z, we have the usual definition of Euclidean division. which is in fact just a lattice problem. It just means the fact that we have a Euclidean division simply means that the covering radius of D is 1/2. Because if I take as a target minus B over A here, I can always find a point in Z at distance at most 1/2. And this point is going to be R, so such that B plus RA is smaller than A over 2. So that's nice. But now if I take a number field, an arbitrary number field and a ring R, what I usually get is that most of the targets are going to be at distance square root D, at least for cyclotomics. So this, again, the numbers are for cyclotomics. So I'm going to be at distance square root D of any element of the ring. And so there won't be any ring element R such that B plus RA is smaller than A over 2. This won't exist, so we cannot have a Euclidean division. So the way we circumvent this is by observing that we don't really need a Euclidean division. We can relax the requirement, and we can allow B to be multiplied by something also, as long as this something is not too large. So if I go back to my reduction, I would like to reduce B2 by B1. But if I can't, maybe I can reduce 2B2 by B1, and I can still get something relatively small. So this multiplicative factor in front of B2 should not be too large, because every time I multiply B2, I'm going to go on the vertical axis. And this I cannot compensate by multiples of B1 because it's horizontal. But if it's not too large, and if then I can reduce this to something small, then I'm still going to gain to reduce the size of my vector. So that's the only requirement that is needed, not a full Euclidean division, but this. And now this x and y, they should exist. I mean, if we count how many of them exist, there should be some x and y that satisfy these properties in any number field. The only problem now that is left is how do we compute them? Yes?
Should we view this as basically a CVP type problem on the principal ideal generated by B? Is that another way of view?
So that would be the regular uses. Here you allow you to change the targets.
A and B is minus
Maybe I'm missing something.
Okay, yeah, I'm just trying to okay, so you're multiplying the, you're also allowing to multiply the target by...
Yeah, I'm allowed to multiply the target by something small, and then I reduce the amount of A.
That's what you mean by ideal one. It's ideal spread by B.
Okay, and so this, I mean, as I said, it's going to be sufficient if we want to.
So this something I could take into a sublattice.
Yes. Yes. We can, I mean, for modules, we have the same thing as for lattices. If we have a good basis of a sublattice, we can, and a basis of a lattice, we can create a good basis of the, good basis of a sublattice. No. A set of short linearly independent vectors and a basis of the module, then we can get a good basis of the module.
So just one stupid thing. I
Yes.
guess the requirement is that maybe y is not 0 or something. I mean, if I set x and y to 0, then
yeah, this one should be non-zero.
okay. Sorry.
Yes.
You were mentioning earlier that you could get away with a factor of 2 in the CVP approximation factor. Is that for the divided by 2 here? You want to be less than A, but could you compensate for that by allowing more choices for the y multiplier?
So this A over 2 is in fact going to be much smaller in what we really do. And I'm not sure this 2 has anything to do with the approximation factor we can achieve. So the no, it's, I mean, I'm going to show you the lattice we consider, and the approximation factor 2 is related to the fact that so we basically can construct, I mean, it's a bit, I don't know how to explain this shortly, but it's not related to these 2. Basically. The short answer is this 2 has nothing to do with the approximation factor we can allow for CVP. Okay, so let's try to see how we can compute this x and y. So I'm going to use a tool that is very useful, that is the log function, and that is defined over k by simply taking the logarithm of the absolute value of every coordinate of my vector. And so this log function has some nice properties. So the log of the product is the sum of the logs. Also, something interesting is that if I take the log of the element of my ring, they are all in a half space. And they all have positive coordinates on this vector 1, which is 1, 1, 1, 1, 1, 1. So the sum of all coordinates of my vectors should be positive, non-negative. And the size of the log is related to the size of the vector, except that it's in the exponent. Okay, so let's try to use this log function here. So I would like to express this in terms of the logs of the elements. The problem is xa plus yb. I mean, log of x times a is something nice. It's going to become a sum, but there is a plus here that is bothering me. So I'm going to replace it by a minus, which does not change anything, but now it helps me think that it's not really xa plus yb that I want, but I just want xa to be close to yb. If I can get xa as close as super close to yb, then in particular it's going to be smaller than a over 2. So it's really closeness things that I want. And this I can express in terms of logs. If you think about the log over the real, if the log of two elements are close, then the two elements also have to be close. And that's the same for our log, almost. So there is one subtlety, which is that if you remember, we take the log of the absolute value. So different complex number with the same module will have the same logs. So we just I lied to you, so we are not going to consider this log function, but we are also going to include into the log the complex argument of the number, so that if both the complex argument and the log of the absolute value are close, then the two complex numbers should be close. And how close is this? So if the logs are smaller than epsilon, roughly the elements are smaller than, the difference between the elements is smaller than epsilon times the size of the elements, which is good because here I can allow a factor a. So I can re-express everything as I want log xa minus log yb to be smaller than some small epsilon. Let's think about 1 over poly in the degree of the field. And log y smaller than big O of log b. So let's draw a picture. I have log a, log b. And I want to find log x and log y, such that log a plus log x is close to log y plus log b. I'm just considering the first condition for them. So let me just write it slightly differently. I'm going to factor what is the input, so log a over b, and I want to find log x minus log y as close as possible to some input vector. So I can't look at all the possible x and y, it's going to be too much. So I'm going to choose a factor base made of small elements. So I'm going to choose a bunch of Ri's that are the log of small ring elements, and I'm going to just look for a path from log a to as close as possible to log b using only this factor base. And all the elements with positive coordinates are going to go for x, and the negative one are going to go for y. So that's what I'm going to do. And the second condition now, that log y should not be too large, simply means that my path, if I first put all the positive coefficients and then all the negative one, I don't want this path to cross some line, which is log b plus big O of log n.
So what was the distinction between positive and negative?
Sorry. So here I get R4 plus 3R1. So it's going to be a ring element, so it's going to be x. And this one is going minus a ring element, so it's going to be y. So this one is going to be y, and this one is going to be x.
Okay.
Whenever I need to take one Ri with a positive coefficient, it's going in x, and a negative one is going in y. And I don't want to cross this line. So this, I mean, is a picture, but it can be expressed in terms of a CVP problem. So here is the CVP instance. My lattice is going to be, so I have an identity block, and on the top of it, so these are vectors. I have R1 up to R d square, so I'm going to say that d square is to make the heuristic somehow work. And my target is this. So let's look at, if I get a vector of L that is close to the target, then the first coordinate here, I should have a linear combination of this that is close to log b over a. So my first condition is met. And the second condition, the bottom part of the lattice, ensures that I'm not going to use too many vectors, because it should be close to 0. And so if I don't use too many vectors, I can ensure that I'm not going to cross the purple line, because my path is going to be short. And so something to observe here is that this lattice L only depends on the number field, and not at all on the amount. So that's essentially the algorithm. The only thing is we don't know how to solve CVP in this lattice L, so that's where we use the oracle. And if we have this oracle, then we get an algorithm that is quantum polynomial time. Because we just compute log B over A, we solve CVP in this lattice, and we get what we want.
And the dimension of the lattice?
Yeah, I'm going to comment on that on the next slide. Let me just mention one more subtlety that I want to say is that, okay, so here the picture was nice, but what if A and B are super far away? And I mean, I'm going to need to use a lot of small vectors, short vectors, to go from log A to log B because they are super far away. And so that's in fact not a problem because we have some units and the units are in H, so I can use them for free. These ones, they do not increase the distance on the one axis, so I'm never going to cross the purple line by using them. So I can always use them to get log A relatively close to log B. So my lattice is in fact this lattice with some units for free here. So this is the algorithm, and I mean now is the heuristic because so I said, okay.
So just at this point where we can tolerate a factor 2?
No, and it's never going to be really obvious why we can tolerate a factor 2. So maybe I can try to say a few things after I comment on the heuristic. So basically what we want, so we have the lattice and the target, and the heuristic we make, okay, sorry, there is a scaling factor because there is two parts in this lattice, and we want this top part to be closer than the second part, so we scale by something large. And the heuristic we make is this. We assume that for any vector of this form with zeros on the bottom part, then the distance of the vector to the lattice is less than square root t. And so we made some experiments for very small dimensions, so I'm not sure if it's working. But we also have some counting argument where we say that, okay, let's assume that I take a linear, random subset sum of these vectors. I'm assuming that the top part behaves random, uniformly distributed, modulo u. And then the probability to be close to B over A, we can compute it, the volume of the ball of radius epsilon divided by the volume of u. And if I can create sufficiently many vectors by doing just linear combination of these things, I have a good probability to find one that is close. And so that's where the d-square comes from. That's when we count, we need to have at least that many vectors to have sufficiently many such vectors and to hope that one of them will be sufficiently close on the top part. Yes?
Say something more about how you construct the RIs. Or like what, so you said something about a factor base. I'm not very familiar with it.
Yeah. Assuming the ring is principal, let's say, which I've assumed for the moment, we just pick random elements of small algebraic norm.
Okay. And this is easy to do. Or I mean,
not necessarily, but that's not what we do in practice. We just pick ideals of small algebraic norm, and this is easy to do, okay. Even if they're not principal. I mean, when we don't want it. I mean, easy, but okay, so anyway, computing the unit, if you want to compute this lattice, you need a quantum computer. Because we need to compute units. Okay, so that's the square root d is there because of the counting argument to have sufficiently many vectors. And that's also where, I mean, the more vectors you have, the... no, I'm not going to be able to explain the approximation. But basically, if we increase the dimension of the lattice, yeah.
So,
yes.
So your CVP oracle is a heuristic as far far as the complexity is concerned, but you've implemented it, right? So how did it work out in practice with you have all the beta RIs and stuff when you do the CVP?
What do you mean? How close were we from the target? Or, I mean,
How painful was it?
it was no. So it was relatively easy to solve CVP. So we could have lattices of dimension relatively big, like 150 or something like that. And it was relatively close to the target as what we were expecting. But in dimension 8, we can make a distinction between square root d and log d. So it's
Deals with this, like with this technique, you could say, well, let's say I get a generator of a principal ideal, and you can shoot units at it to get a small one, but then if you get your beta RIs, you can go maybe below the size of a short generator, and
yes.
because you'll get something that's no longer a generator of your ideal, but that could be bridging the gap between the actual short vectors in your principal ideal and the short generators. So if
yeah, that's the point. Like having the R's allows us to have something smaller than the short generator.
So if that were to be efficient, then you would find shorter vectors than the short generators.
Yes.
So that'd be cool.
Yeah. Yeah, I mean, it's the same.
Those are division. You do not end up in the ideal you started from.
Oh, yeah.
Oh, yeah, there is.
Minus signs.
Yeah.
Oh, so
But
maybe that's not that cool. Sorry.
But that's the same techniques we use for ideal SVP also. Just shift a bit instead of putting zeros there, put some 3, 3, 3, 3 so that you get something only positive in the end,
Yeah,
so that there is no division.
Yeah.
But yeah, so I mean, what we do is implies an efficient, I mean, if it was efficient, we would have super solver for ideal lattices. Yes.
This is needing basically to solve CVP with pre-processing, but in dimension d squared.
Yeah, so the preprocessing won't help because if we want a constant approximation factor, even with preprocessing, we still need exponential time to
Right.
solve.
I mean, as far as we know.
As far as we know, yeah. But
Back to the mysterious factor 2. Are you saying that the dimension, this d squared dimension, like if I want factor 2 to work, the d squared has to increase? I need more elements in order to handle a factor 2, or like for this fixed lattice, a factor 2 is okay?
for this fixed d squared factor 2
Okay.
should be okay. So it's strictly smaller than factor 2.
Sure.
Okay, and so all this counting argument is related to what Leo and Benjamin are going to discuss about this afternoon. Okay, let me just maybe skip what I didn't say. So there are other techniques that we need to use to have a full proof of the algorithm. So we need to use class proofs, a lot of things. Let me just conclude on what we get. So we get an algorithm that gives us an approximation factor exponential only in the rank of the module and quasi-polynomial in the degree of the number field. And so the runtime again is only if we have this oracle, so in a lattice of dimension d squared. So what if we want to run this algorithm in practice? Well, we need to instantiate this oracle. And if we do that by using a generic CVP solver, what we get is very bad. So this is the algorithm we would get compared to BKZ. So this is what we can obtain with BKZ. And our algorithm will give us something exponential in k, but in time exponential in d squared. So this is absolutely not to be used by replacing the oracle by some CVP, generic CVP solver. And so this brings me to my main open question, which is, can we do better than just instantiating the CVP solver with generic one? Can we maybe reduce the dimension of the lattice L? If we could reduce it to D, sub 2 of D, then we would move on the BKZ trade-off. So no better, but no worse. And if we could use the structure of L, then we could also hope maybe to get something better by using the symmetries of the lattice L and things like that.
Sorry, what's the advantage then of using this over BKZ?
It's just, I mean, yeah, no practical advantage at all. The only thing is that we have factored all the difficulty of solving SVP in modules into just the difficulty of solving CVP in one fixed lattice. It's a reduction, essentially.
Yeah, okay, and also in theory. So also in, it's not just a practicality issue. Also in theory, you.
Let's say for this particular lattice there is a magical CVP solver, then maybe something.
Yeah, so it's a reduction. Yeah. Okay.
Yeah, it's something.
And you get a much better approximation factor, right? Because it only depends on the
I mean, we
rank.
get the same approximation factor as BKZ with block size.
With block size.
So the idea is that perhaps one can find a better oracle
Yeah.
than a generic algorithm.
Yeah.
So this is the
So that's, yeah. We reduce the difficulty to just one lattice, CVP in one lattice. So, I mean, yeah, that's the main open question. Can we solve maybe CVP in this lattice? Is there some efficient way to do that? And just let me just mention that there are lattices for which this is NP-hard. Maybe it's easy, maybe it's NP-hard, and I mean, for the moment, we just don't know enough. And the second open question also I wanted to mention is, can we generalize this LLL to BKZ to get all the trade-offs? So we already have part of the reduction, which goes from rank K to rank beta. This is Noah and Tamalika. But then the challenging part, which is open to what I know, is can we do any sieving or enumeration in modules of rank beta? And so, I'm sorry, right? Thank you.
Thanks for all the questions. If you have more, let's take them offline. We have a break until 11, so we'll resume in 22 minutes for the next one.
So what's your guess? Or the